right. Good morning, everyone. We're here today for the June summer's webinar series. And we're speaking today with Peter Caulfield. Most of you know very well. So Peter was an undergraduate at Penn University here in Pennsylvania. They did very well. And he's been at Penn for this is going to be 4 years.
Almost 4 years, yeah.
Good. Peter's multi-talented guy, does many things, including playing the piano. He's also an artist, draws and paints, right?
Mm-hmm.
But today he's going to tell us about more interesting things.
Depending who you ask.
Putting in pressurized porous elastomers.
Yeah.
Peter?
That's right. All right. Thank you everybody for being here. I really appreciate it, especially Prashant and my committee. Thank you for making it. And Professor Ponte. All right. So I'm going to start off by, let's see if this works. There we go. Skipping ahead to the punchline to tell you what we're talking about. Okay. So here's the fundamental idea of what we're looking at. So imagine you have some sort of rubber and you have pores randomly distributed inside of that rubber. And now you start compressing that material. So you start here, we're just doing some uniaxial compaction. And what you'd expect is that as you start off doing this, all of the pores on average are going to compress more or less in the same kind of way. So this is just schematically, but you see they're all sort of squishing in the direction that we're compressing the material. But what we predicted is that after sufficient compression, what you get is something that's no longer a uniform deformation. The material splits up into these bands where the material is shearing first one way and then the other way, alternating back and forth. So that's what we're talking about with twinning. So with that background, now we can get into some of the more details about what we're talking about here. And I encourage you, if you have any questions anywhere throughout, please ask them. I want to make it so that hopefully you can understand what we're talking about here.
The compression is isotopic.
No, so this compression is just uniaxial compaction. So we're keeping this direction the same, and we're just compacting in this direction.
So it's like a so let's say we are compressing in the one direction. Is lambda 2 and lambda 3 kept equal to 1?
Yes, you could do that. And in fact, this is just plane strain. So this is a cross section of the material. So lambda 3 into the board is fixed at 1 anyway. And then here we're just fixing lambda 2 or lambda 1 and compressing the other way. But you could flip it because it's isotropic in plane. So you could compress in any direction and you get the same result. Yeah. All right. So just a little bit of background. Why are we interested in this type of material? Probably a lot of you know, especially the ones who during Rainey's lab, you look at some things like this. People are interested in rubber with some holes in it for a lot of applications in various types of settings. So one is that people have discovered you can get auxetic behavior by creating materials where you place holes in specific shapes and orientations. You can get these sort of metamaterials where people are interested in their acoustic properties. You can guide waves in different directions, with band gaps. And another thing, which is really the inspiration for why we're looking at this type of material, is as soft actuators. So people have taken rubber, you put some cavities in it, you control the pressure in those cavities, you get some sort of deformation, and then you can use it as, in this case, a gripper or a muscle or something along those lines for robotics applications. So that's why we're interested in these things. Now let's talk about what twinning actually is, because that's not something that you normally see in this context of porous elastomers. The more classical places to see it, one is shape memory alloys, something that many of you maybe have seen it in. So this is just a picture, close-up at the interface between the austenite phase and the twinned martensite phase in one of these materials. And what you see in the martensitic phase is these fine layers alternating back and forth, and those correspond to alternating directions of the crystals inside there. And you get these very, very fine layers, which is what we mean by twinning. You can also see something similar in liquid crystal elastomers, where you have some sort of director inside the elastomer, and what you see with these fine layers is alternating orientations of that director inside of the elastomer. So you have these domain formations in these laminar shapes. So physically, that's what it is. Mathematically, you can think about it as a minimizing sequence for the energy. So you have basically taking the limit as the size of these domains get smaller and smaller and smaller, and that's what mathematically corresponds to twinning. And so that's something that's been looked at over the years. When can something like this occur? Well, it turns out you can use this expression here, loss of strong lithicity, to tell you when you can get something like this happening, which is just a condition on the tangent modulus of your material. And so if you ever fail to satisfy this condition, then you have the possibility for an instability, which could result in something like twinning. Once you have something like this, once you lose strong lithicity, how do you go about figuring out what sort of behavior you're going to get? Well, what you do is you construct a relaxation of the energy. Now, of course, in finite elasticity, we're working in kind of a high-dimensional space, so it can be hard to picture what's going on. There's various notions of convexity. But this is just a schematic, simplifying things down to one dimension where things are a little easier to look at, a little more intuitive. So imagine the vertical axis here is your energy, and then this horizontal axis is kind of your deformation. You can think of it as maybe a rank 1 direction in deformation space. And so in that kind of a case, in this one dimension, what the loss of lithicity would correspond to is a loss of convexity in your stored energy. And so you can see here we have some sort of classic double well type potential. The relaxation in that case corresponds to convexifying this non-convex energy. So you just cut across the bottom here to create something that's convex. If you look on the right-hand side, this is a schematic, again, in one direction, of what the stress would look like corresponding to that. And so this double well here in the energy corresponds to a non-monotonic stress. As you change the deformation, you go up, but then you come down again before continuing. When you do this relaxation, which is the convexification for the energy, for the stress, it corresponds to cutting across that non-monotonicity so that you get something which is no longer decreasing and just cutting across the middle. And in this one-dimensional case, that corresponds to something called equal area construction, where you have the same area above this line as you have below this line.
Peter, I
Yes.
have another question here.
Yeah.
This is not an area that I have delved much into at all, but loss of strong electricity is different from loss of electricity. Maybe one is a subset of the other.
Yes, exactly. So the difference is in strong electricity, you have this strict inequality here. In electricity, you would just have a non-strict inequality.
Is the definition also a little different? That is, determinant of L, I, J, K, L, M, J, and L is greater than 0.
Yes.
Or greater than equal to 0. That is loss of electricity. Whereas when you introduce the Mi and Mk vectors like you have here, up there on this slide, that is strong electricity. Am I right? Am I wrong on this?
Let's see. So yes, you can think of electricity as being a condition on the determinant of the acoustic tensor. When you do that, so the acoustic tensor, yeah. So what you said there, I think is correct, and it's equivalent to this. So basically, this part here, you could say, is creating the acoustic tensor, and then the other two vectors. Then you have a second order tensor. So yeah, the other two vectors are just checking for positive definiteness of the acoustic tensor. Yeah. Does that make sense? That makes sense. Okay. Okay, so this is just schematically to give you a feel for what's going on. Now turning to porous elastomers, people have been looking at instabilities in porous elastomers for a long time, and actually all the way back to the 60s, Blatz and Co did an experiment where they took rubber foam, so rubber where you have these pores in it, and they did experiments on it and measured things and came up with some phenomenological model for the stored energy function for that material. And so they published that, but people later looked back at this result and said, oh, actually, this result loses strong lithicity for certain deformations. And so it has the possibility for these types of instabilities. Later on, people looked, so that's in kind of a random case, this foam. Later on, people looked analytically at other types of elastomers, and first of all, this periodic elastomer. So you have just a periodic arrangement of these pores, and computed what the effective behavior of this material would be. And again, they found that for certain deformations, you could lose strong lithicity for the response, the macroscopic response of that material. This was something that was predicted first analytically, but later on people looked at things numerically and also experimentally and saw that yes, they found that there's this instability and computed what happens after the onset of that instability. In this case, you don't get something like twinning, but you do get something where instead of being sort of uniform deformations going on, you break up into where the pores compress first one way and then the other way. And that's something that people saw both numerically and then, yeah, in these experiments, which maybe a lot of you have seen these kinds of things that are a little bit famous. But that's in the periodic case. So it's still open what happens in the aperiodic and the random case. Okay, with that background, now let's get into a little bit of the framework of how we're going to look at this. So what we want to do is figure out the macroscopic energy of these elastomers. So first off, what's the local energy? Well, we can say that the matrix has some energy which we'll call W1, function of the deformation gradient, and that means the local energy of the material. You can just write like this, where this theta is just telling you whether you're in the pore phase or in the matrix phase. So this is the local energy of the material. Then we can define the homogenized energy basically by the principle of minimum potential energy. So we want to apply some displacement boundary conditions on the boundary of the material. And then we want to try to minimize the average energy over that material. And that's what we'll define as the homogenized energy. Now, what you'd expect is that, so the Euler-Lagrange equations for this are basically, if you're sufficiently close to the undeformed configuration, F equals 1, then you basically just recover linear elasticity. And so what you'd expect is that there's some unique solution when you're sufficiently close to the undeformed configuration. But once you get away from there, things become nonlinear. There's the possibility of multiple solutions to the stationary conditions of this. And that gives the possibility of maybe you can have some sort of instability. So in general, you can generalize this to you want to take the infimum of this over all possible things. And this infimum is what allows for the possibility of these minimizing sequences as the solutions. And so this is what we'll call the mesoscopic or the principal solution for the energy, the thing that's continuous with the solution you get close to F equals 1, or the identity. And then this is what we'll call the macroscopic or relaxed solution. All right, so these things, computing things from these definitions is a bit difficult. It's not really the best way to go about solving these problems. But it turns out that something you can do to get an estimate at least on this macroscopic relaxed solution, you can do that in terms of your mesoscopic principal solution by computing what's called the quasi-convex envelope, the quasi-convexification of the function. And that's something that is at least gives you an upper bound, but is postulated to actually be the exact result for this energy. Now, what is the quasi-convexification? Well, as I said, when you're working in finite elasticity, you have high dimensional spaces, there's various notions of convexity generalizing what we're, standard convexity that can be useful to think about in this case. And so these are three important things. They could be a little bit complicated, but we'll just try to get the main ideas. Probably this one is the simplest one to make sense of, which basically just says that your function is convex along rank 1 directions in deformation space. You have this second order tensor F, but if you're convex along rank 1 directions for that, then you're rank 1 convex. Polyconvexity is maybe the next simplest to understand. That's if you can write the energy as a convex function of F, its adjugate and its determinant, then your function is polyconvex. And then quasi-convexity has perhaps the hardest to understand via the definition. Intuitively, what it means is if you do some sort of displacement boundary value problem on your material, such that you apply some displacement which would allow for a homogeneous strain throughout the material, that homogeneous strain will be a minimizer for the energy. And so you can see that if you're quasi-convex, it wouldn't allow for these types of non-uniform strains throughout the material when you apply a macroscopically uniform strain. Okay, so that's one thing that's important. Another important thing is that these conditions, polyconvexity and rank 1 convexity, are a little bit easier to check and a little bit easier to work with because they're in terms of our standard kind of notions of convexity. Whereas this one is based on this volume integral over some, domain D. It's a little bit trickier to work with. It turns out, though, that there is something you can say about how these are related to each other. So, of course, let's say this. So if something is polyconvex, that implies it's quasi-convex. Something's quasi-convex, it implies it's rank 1 convex. And so that means if you compute the rank 1 quasi and polyconvex envelopes of a function, you can order them in this way. And so that's something that's going to be useful, since what we're interested in is the quasi-convex envelope. Okay, so now let's say, using all of that, what's going to be our approach for trying to compute the relaxation? So we want the quasi-convexification of our principal solution for the energy, as I said, and we have this system of inequalities. So what you can see is, first of all, if we get the rank 1 convexification, that at least gives us an upper bound for the quasi-convexification. But if we can compute this and show that it's also polyconvex by this sort of sandwich, that means it also must be quasi-convex. And so in that case, the rank 1 quasi and polyconvex envelopes are all the same thing. And so we have the quasi-convexification. And so that's going to be our approach for looking at this. That, of course, begs the question, well, then how do we get the rank 1 convexification? There's a procedure which has been published for how you go about this, which is a sequential lamination. So basically what you do is you sequentially allow the material to break up into these laminar domains, and you do that over and over and over again, and eventually, once you converge, you get something which is rank 1 convex. And so this allows you to build up your rank 1 convexification. And these parameters here, this C would be the volume fraction of the layers in that laminate, so you're trying to minimize over the size of each layer. This N is the orientation of each layer, so you minimize over that. And then this W is telling you about the deformation in each layer. One thing you can see in here, this is the deformation of one layer, this is the deformation in the other layer, is that they differ by this rank 1 tensor here. And if you remember perhaps from continuum mechanics or from elasticity, if you're going to have something that's discontinuous, a discontinuous deformation, then you can only differ by something that's rank 1. And so this builds that in to its form. Okay, so that's how we can go about getting the rank 1 classification, and then that's going to be our approach for the problem. Okay, now let's try to look at the actual problem at hand. So this is a schematic of the type of material that we're looking at. It has these pores in it. We're going to model the matrix behavior, this rubber, as being incompressible neo-Hookean. Inside of that are isotropically distributed, these cylindrical pores, which are all aligned into the board, but randomly distributed in plane. And we're going to think of them as being polydispersed, meaning they're all different sizes. They're not the same size. And then we're going to subject this material to plane strain in the plane orthogonal to the pores. So it's just a two-dimensional loading. All right, that's the material. Now, it turns out there's already an estimate in the literature. So Dr. Ponte computed this with one of his previous students a little while back. So we have an estimate for the principal solution or the mesoscopic solution for the stored energy function of this material. Because it's isotropic and we're just doing this two-dimensional deformation, therefore you can characterize the energy by a set of two invariants. Here we're writing it in terms of the in-plane principal stretches of the material. And you can write it in this form in terms of some various parameters. This F naught here is your initial porosity of the material, and this mu is your shear modulus of the matrix space. All right, so we have that principal solution. When they computed this, they noted that indeed for certain deformations, you have loss of strong lipticity, meaning that there's the possibility for instabilities once that happens. And so that's what we're going to look at. This is what the energy looks like if you plot it as a function of lambda 1 and lambda 2. On the left, this is the 3D surface. On the right, these are the contours. And what you see is that for sufficiently small lambda 1 and lambda 2, you have this kind of bump in the energy, which kind of, based on our intuition from that one-dimensional case, could tell us that maybe there's something strange going on here. And indeed, if you compute the loss of strong lipticity for this material, and you look at the boundary of that, it does occur around the area where this bump in the energy is.
More like a dent.
A bump, but then it's, yes, there is. So the energy here actually, it rises in this regime, and it's a little bit hard to show. This is something that Dr. Penn and I've talked about a while. It's a little hard to show this 3D surface in a two-dimensional plot, but the energy in this regime not only rises up, but it actually gets kind of like a crease like this in it. So it's like, it's not just that there's a rise, it's also creasing, which is like really weird, really bad, you know, you could say, as far as stability is concerned. And that's like, you can kind of see this like spikiness here. That's where that dent in the energy occurs. So it's not like this, if that makes sense.
It becomes non-convex, right?
Well, yes. So the energy,
In this space.
right, in this space it becomes non-convex, but you know, this is just a projection from the higher space of second order tensors. And so convexity in this subspace isn't necessarily what you want to look at. We'll see some other things where, depending what subspace you project down onto, it does correspond to loss of convexity in that subspace, but that isn't precisely the condition you want to look for. Anyway, yes, so, but intuitively, that lack of convexity also has some alignment with the loss of elasticity. Okay, that's the energy as a function of lambda 1 and lambda 2. Of course, there's various sets of invariants that you could choose to characterize things. And so another common set that people use would be I and J, where J is the determinant of F and I is F dot F. If you plot things as a function of that, again, you have this kind of rise in the energy for sufficiently compressive loadings. And what you see in this space is that in the strongly elliptic regime, the energy is an increasing function of I, whereas in the not strongly elliptic regime, the energy is a decreasing function of I. And then loss of ellipticity in this space corresponds to the point where the derivative is equal to 0. Okay, so that's the principal solution for the energy. Now let's try to go through that procedure that we talked about to try to compute the relaxation. So step one is try to get the rank 1 convexification. And so we go to that definition, we try to compute the minimization, and we get this result here. So in the strongly elliptic regime, you just have your same energy that you had before. I didn't mention it before, but you have this incompressible matrix with these pores in it. Of course, if you compress it sufficiently, the pores eventually will close, then you have an incompressible material, so you can't compress beyond there. So in that regime, you have infinite energy. And then in this regime where you did lose ellipticity, you can write the result in terms of your mesoscopic energy, but where now, instead of evaluating it at the macroscopic I, which you apply to the macroscopic F dot F, you now have this alternative prescription where you evaluate the energy that's based on your volumetric deformation that you applied. And what is that? Well, it turns out that is the solution to the point where the derivative of the energy goes to 0, which, as we just saw, is the loss of ellipticity boundary in that IJ space. And so you basically just go over there, grab the I that corresponds to the loss of ellipticity, and plug that in for your energy here. So that's one lamination. In theory, as I said, you might need to do this multiple times because you're only checking rank 1 directions, but you have this higher dimensional space. But it turns out that this one lamination is sufficient to make this rank 1 convex. So that means that this is a rank 1 convexification. We want the quasi-convexification. So as I said, the next thing to look at is if we can show that this thing is polyconvex. It turns out that in this lower dimensional space, sufficient and isotropic material, sufficient conditions for that is that your function is convex in I and J, and also non-decreasing in I, which we see corresponds to the fact that when we looked at the energy before, the not strongly elliptic regime is where the energy was decreasing in I. If we look at what our energy looks like now, after this relaxation, you can see that in this regime where we used to have the loss of ellipticity, now you can see that the energy just becomes constant as a function of I, which makes sense because we're now evaluating the energy basically at this boundary for any I within here. So that means the energy is now non-decreasing in I throughout this whole regime, meaning it is polyconvex. So that means that this thing is our polyconvexification as well as our rank 1 convexification. So by that system of inequalities that we had before, that means we do have the quasi-convexification, so the relaxation of our energy. Okay, this is just summarizing again. An important thing to note here is that when you're inside this relaxed region, the twinned regime, the energy is now a function only of J bar, so the macroscopic volumetric deformation. So that means you have 0 shear modulus, and you're behaving like an elastic fluid in that regime. So you have some bulk resistance, but no resistance to shear deformations in that domain. Okay, This is looking at that macroscopic energy as a function of lambda 1 and lambda 2, like we looked at before. And what you see is that bump or dent in the energy that was here under generally compressive lambda 1 and lambda 2 has now disappeared. And when you look at the contours of the energy, you see that now they are exactly, you can take my word for it, hyperbolae, contours where lambda 1 times lambda 2 is equal to a constant, which corresponds to the fact that the energy is only a function of J bar in this regime. Okay. You can get the energy, but from this lamination procedure, you can also get what you could say microstructure, but really mesostructure, because this is at a scale that's larger than the pores, but smaller than your overall material. And this is just a schematic. You wouldn't expect a material to actually look like this, but for schematic purposes, this is good enough. So as I said, there's three main parameters that you're looking at. One would be the volume fraction of each layer of the pore, of each layer in the laminate. Another one is the orientation of the layers. And then the third would be the deformation in each layer, which you characterize by the spectra W. So once you find your ISC, which is that place where you evaluate the energy in the twin regime, you can compute the magnitude of W in terms of that and in terms of your layer orientation. And you also know what the direction of W has to be. You can get the layer volume fraction, again, as a function of the layer orientation. When you have this, that's actually sufficient to make your function rank point convex. And so in particular, what that means is that the layer orientation is arbitrary. So you can satisfy all of the optimality conditions for any orientation. It'll just result in a different deformation in each layer and in a different volume fraction of each set of layers. So you could have something that looks like this, but you could also have something that's flipped the other way, where now you're arranging it vertically or anywhere in between. Okay, that's what the mesostructure looks like. You can look at the moduli. So here we're plotting things for over here, uniaxial compaction, like that diagram that I showed in the very beginning. Over here, this is hydrostatic, so lambda 1 equals lambda 2. And you can look at how the macroscopic moduli change as you undergo a deformation. What you see here is sort of as you'd expect, these moduli are increasing as we're compressing, but you see the shear modulus, which if you remember, this material, this instability was based on its shear behavior. So the shear modulus decreases till you get to the point where the shear modulus equals 0. That's where loss of elasticity occurs with the principal solution, and its dotted line, which is the principal solution, then goes negative. It has a negative shear modulus after that point. The relaxed solution, which is the solid line, just has 0 shear modulus once you get beyond there. You can see the other moduli also become softer. The material generally softens once you hit this boundary. So you're increasing, but then there's a drop in these other moduli as well, even the non-shear moduli, once you get to the twin regime. And you can see that in both types of loadings. Okay, now we're going to turn back to look at the energy again. We're going to look at particular cross sections of the energy, and we're also going to compare them with a different estimate in the literature for this type of elastomer, so an isotopic elastomer with, this is based on a different strategy for computing the effective behavior of this, which basically corresponds to creating a hierarchical laminate where you layer rubber with, in this case, pore space, first this time, and then do it again, do it again, do it again. That's why it's called sequential lamination. There's, you get a nice tidy formula when you do that, but when they published this, they noted that the equation for the energy, the result that you get is polyconvex. So it doesn't have the possibility of these types of instabilities that we saw here. And so we'll see what that looks like when we compare it with ours. We're going to plot things here, these sort of, you can think of it as cross sections of the energy for a constant value of the macroscopic J bar, so your volumetric deformation, and then in terms of this, which is basically a measure of how much shear is in the material. All right, so this is for actually a tensile J greater than 1. And what you see in that case is that the sequentially laminated result, the principal solution, the relaxed solution, they're all on top of each other. There's basically no difference between any of them. And you see that it looks like a nice convex, nice function. If you go a little, not tensile, but just J bar equals 1, so no volumetric deformation, again, everything's basically on top of each other. And again, it looks like a nice convex potential. as you can start to compress now, so this is for J bar equals 0.5, you see that the sequentially laminated result, which is this dashed line, is still a nice bowl at the bottom, but this principal and relaxed solution are starting to flatten out at the bottom. So you're approaching something that is a little bit less convex than it was before. And if you continue to compress, you get something which in this subspace becomes this classic double well kind of potential. So you can see that the principal solution, the dotted line here, has this double well where you rise and fall here. The relaxed solution corresponds to just the convexification in this subspace, so you just cut straight across the bottom of that. And then the sequentially laminated result is stiffer than both of those results and is again just nice and convex. You can compress even further. In this case, this is for an initial volume fraction of 70% porosity. So J bar equals 3 is the point where the pores close. So this is right on the pore closure boundary. You can see that the lack of convexity in the principal solution has continued to get even worse. So you have this very strong thing. And again, this is that sort of dent that we were talking about before, this sharp point in energy. The relaxed solution, again, just cuts right across the middle. And in fact, the sequentially laminated result doesn't show up here because it's infinite, it predicts infinite energy on the pore closure boundary. So you can see how those relate to each other. In this subspace, it looks like your classic, double well potential cut across the bottom, but just remember that it depends on what subspace you plot things in. That's the energy. Like before, we can say, well, what happens to the stress? So here we're going to look at the normal Cauchy stress difference. So that's a measure of how much shear stress you have in the material, as again, a function of the shear deformation in the material, and look at these 3 different estimates. And it turns out that when you plot things in this way, the sequentially laminated results just give the same curve no matter what. So it's always this dashed black curve here. And for sufficiently high values of J bar, our results also align perfectly with those. But as you start to compress a little bit, you start to deviate from that. And eventually you get to something which becomes non-monotonic. So you rise and fall and then rise again. And the relaxation in this case corresponds to what we saw before, where you cut across that non-monotonicity and make it just flat there. And it corresponds to that equal area construction. So the area of both of these spaces is the same. And you can continue to compress, get something which is less well behaved, but again, you just cut right across the middle. An important thing to note here is that you have this line which is exactly at T11 minus T22 equals 0, meaning 0 shear stress in the material once you're in this relaxed regime, which is what you'd expect from the fact that it's behaving like an elastic fluid. All right, so there's that. Now, all of this has been in the context of a material without pore pressure. I said in the title, pressurized pores. So we'll try to get into that in the time that's remaining. In general, this could be a hard problem because you might need to do the whole homogenization procedure from the ground up. So you need to come up with a new estimate for your principal solution. You need to check loss of elasticity in that solution. You need to do all of these various types of convexifications, check everything, see what happens. But it turns out that because we've modeled the matrix phase behavior as being incompressible, if you look at the finite elasticity boundary value problem that this corresponds to, basically the effect of applying pressure in the pores is the same as the effect of applying tension of that same magnitude on the boundary of the material. And so what that allows you to do is write your expressions for the energy with pressure in the pores, just in terms of the energy without pressure in the pores. So you can write it like this. This is your unpressurized energy. This is your pressurized. And then this term here is something that's based on how the pressure in the pores evolves with the deformation, which is just a function of your volumetric deformation. This is something that you can show is the case for the mesoscopic energy. But it turns out if you check do all that stability analysis again, you get an analogous result for the macroscopic energy as well. So again, you can write the effective macroscopic behavior for the pressurized material in terms of the macroscopic relaxed behavior for the unpressurized, plus just exactly the same term on the side, again, based on the pore pressure evolution.
So, Peter.
Yes.
The pressure that you are prescribing in the pores,
yes,
is the pressure prescribed from outside?
So it could be anything. This, in fact, maybe I'll just go to the next slide. So this W of J takes this form. This C is your pressure evolution potential. So take the derivative of this with respect to J to get the evolution of the pressure as a function of J. And that could be something like the ideal gas law or another equation if you have it for, an actual material that's inside of there. But you could pick whatever function you want. And so you could also choose it to be something that's a constant function of J bar, which would correspond to the case where you have some sort of controller controlling the pressure throughout the deformation. Like you had a pump or something. So it could be either.
The way I'm thinking about it is are the pores closed or are the pores open?
Yes. Yes.
If the pores are closed, and if you have, say, like an ideal gas inside there, then the usual PV equals MRT.
Exactly.
The volume is going to be the free energy and so on.
Right. Yeah.
Right. Whereas if it's open pores and you have a pressure that is prescribed from outside, like it would be done in some pneumatic device that is used to control a robot or something, right? So then the boundary condition is different, right?
Yes, the boundary condition is different. But we're not concerned so much with the boundary behavior of this thing. You can do something on the boundary to try to get the material to behave the way you want. We're more concerned with the bulk behavior of the material, especially because we're only doing this two-dimensional problem anyway. So if you want to prescribe pressure, you have to prescribe it on this surface that's in 3 directions. So what's going on there? I don't know. You can maybe do an experiment where things work out. But in theory, you could either have cap off the ends and have some gas fixed inside such that it behaves, let's say, like an ideal gas, or you could have some pump fixed to the end that allows you to control the pressure throughout the deformation. But you're only concerned with the bulk behavior anyway. Yeah, and either of those cases or any other type of pressure evolution law would fit into this model. You just choose your C for that. The only thing I will say is that in order for this instability and relaxation analysis to hold the way that I showed it, you do need this potential to be a convex function of J bar, which is what you normally expect if you have a normal, either gas law is convex and others for sorts of state equations would also be convex. And it doesn't need to be strongly convex, so or strictly convex, I mean. So in particular, a constant function also fits into this definition. All you need is it to not be have a negative, or you just need it to be convex, not strictly convex. Yes.
Follow up with question. So the rubber is incompressible, simply incompressible. And so if carry the pressure inside the pores, the corresponding to essentially fraction from the boundary. Just get that question simply, And so that's actually what we use, right? To get this function J bar.
Yeah.
To relate the solution. The pressurized force is a solution.
Yeah. Okay. So you can do it for general. As I mentioned at the beginning, the motivation for this was people having actuators where they control some sort of pressure in the system. And so the particular case that we're going to look at is where you control the gauge pressure in the pores. So as I showed here, you can also account for some constant atmospheric pressure, let's say, outside of the material. And so then you can write the energy in the case of some prescribed gauge pore pressure like this. Okay, now quickly let's look at an example of what that looks like if you do an experiment with this. So again, we're plotting things in terms of lambda1 and lambda2. And what we're going to do is fix some traction boundary conditions on the surface of the material and then depressurize the pores and see what deformation path you get as a result of this procedure. And so each of these dots here corresponds to one increment of pressure going down. Here on this left side, what we're plotting is if you apply Pure-Kirchhoff type tractions, so tractions in the reference configuration, which corresponds to a fixed load on the material. And so what you see is if those are both equal to each other, what you get what you'd expect, which is basically you just compress down lambda1 equals lambda2. When you hit the twin boundary, what you see is that, maybe it's hard to tell, but these points do get further apart. So you do have softening, but you just continue down the same path. Now, alternatively, you could apply a different type of traction boundary condition. So you could apply Cauchy type tractions, meaning tractions in the current configuration. And if you do that, you get something that looks similar up to the point of twinning, But once you get into the trained regime, remember, you're behaving like an elastic fluid now. And so if you apply hydrostatic pressure to a fluid, the shear deformation is indeterminate from that because there's zero shear modulus. And so once you get into this regime, you could go in any direction down that path. It's not, according to the energy, there's no preferred direction for you to travel. So there's a difference based on if you apply Gillen-Kirchhoff type tractions or Cauchy type tractions. Now we can look at what happens if you don't apply the same tractions on both sides of the material. So if you apply a little bit of a stronger compression in this direction than in the other, you get something that's a little bit off hydrostatic. But remember, we're applying hydrostatic pressure in the pores. So what you'd expect is, even if you're a little bit off hydrostatic here, the effect of that pressure would be more or less hydrostatic. But due to the fact that the material softens in shear as you approach this trained regime, while you start off, compressing in both directions, eventually you start bending and you start actually expanding a little bit in one direction while you continue to compress in the other. And that occurs up to the point where we get into the trained regime. Once you get into there, the fact that this has to behave like an elastic fluid basically forces you to follow this linear path through that trained regime. So you stop bending and you start just going straight down here. And you can compute the slope of that path based on the magnitude of your two tractions that you apply. On the other hand, we can see what happens when you do Cauchy type tractions. Now, if you apply different tractions on the two surfaces, you're no longer applying a hydrostatic pressure to the material. Fluid, of course, an elastic fluid can't support any shear stresses. And so even if you apply different tractions on the surface, and you can never get inside of the trained regime. So you come down and just follow along the edge of that trained regime. And as you see, this corresponds to a big change in shape. You start compressing both directions, but then expanding this way. You can see the same thing if you switch the direction of the tractions on both sides of things. One further thing to emphasize this point about the difference in the type of tractions you apply. Over here, we're applying just a tiny difference in S1 and S2, so the tractions in the two different directions. And what you see is you just get a small perturbation in the deformation path that you get if you applied hydrostatic tractions. But if we do the same thing in the Cauchy type tractions, what you see is that because you can't support any normal stress difference, while they start off very close, they end up in drastically different configurations because you have this very slight, ultimately infinitesimal difference in the applied tractions on each surface. So it has this kind of interesting behaviors, these big changes in shape, this high sensitivity to the loading conditions. Okay, with all of that said, thank you very much for your attention. I hope it made at least some sense. This is just, again, a schematic of approximately what the result looks like, and I'm happy to take any questions that you might have.
Questions?
Yeah.
Thanks for the presentation. Nice. I'm a little bit confused on the linearization process that you do. I'm trying to understand how to decide or what's the result in terms of domain that you get from the linearization. The number of domains that will depend on conditions, or you said, for example, the direction of the linearization, the arbitrary. What does it mean, the arbitrary? Doesn't that depend on the...
In general, you would expect that it would, but in this case, it turns out it doesn't. So when you apply your macroscopic deformation, any orientation of the layers you can get a configuration which has the same energy and which is rank 1 convex. So if you follow those conditions that I showed for those mesostructural parameters, you get the same energy no matter what, as long as you choose your volume fraction of layers and your deformation to correspond with your orientation of the layers. Yeah.
So they're not really affected by...
Well, they are affected because you are a function of your macroscopic J. So the orientation, volume fraction deformations are a function of that. It's just that you can choose any orientation for any boundary condition, and then the other parameters will change. Yeah, C and the W.
I have a very like simple question, but so as I understand, you might have like porous material, then when you compress it uniaxially, you might see the material like this,
Mhm.
where you will have segments, such that in each segment you will have like a certain application of pores.
Mhm.
So my question is, how large the width of those segments compared to the average size of the pores? Should it be like much larger than the pore size? Should it be comparable?
Mhm.
Like, I understand this is just a schematic, but
Right.
to expect that we can do that.
Yes. So mathematically, this actually corresponds to an infinite separation between homogenization corresponds to an infinite separation between the length scale of your microstructure and the size of your specimen. And in this case, you would have basically two of those separations of length scale. So that the difference between the size of the pores and the size of these layers mathematically should be infinite. And the difference between the size of these layers and the size of your macroscopic specimen mathematically should be infinite. One way you can see that second point is, I drew this here. If your material is shearing back and forth like this, that doesn't quite satisfy your boundary conditions. If you, imagine you fix the boundary here to be, not deforming. If you made those layers smaller, you get closer, and that's why I said it's like a minimizing sequence. As you get smaller and smaller and smaller layers, you start to satisfy the boundary conditions. In real life, I don't really know. It would be very interesting to see an experiment that somebody showed this kind of thing occurring. Probably somewhere between 1 to 2 orders of magnitude would be sufficient to see this kind of thing. How far you can push it, I don't know. Yeah.
Sorry, just to finish on this one. There's something that you can say about the size of these domains, and that is, so you draw an interface, right, between these domains. That interface will require some additional energy.
Yeah.
That is not being accounted for, right? And so, in reality, the length scale of these domains would be determined by some additional energy, surface energy, for these domains. Similar to what happens in memory of systems that also exhibit domain information. But that, would require estimating the energy of these, much as it costs to use these terms. Discontinuities in the solution of these surfaces.
Yeah.
And there will be a boundary layer near the boundary.
Yes.
Far away.
Exactly. In a real specimen, you'd have a boundary layer at the edge where it isn't doing this kind of thing. Yeah. Yeah.
I also had a follow-up question. At the beginning, I think in one of your first slides, you showed the schematic of the thing, and you said that, okay, you're controlling the horizontal direction, and you're fixing the other direction.
Right.
But in real life, I expect that you might have some boson effect, I guess.
Yes, exactly. This is a very good point. So you can do two different experiments. One would be uniaxial compaction, where you fix the deformation in this direction to just be, not deforming at all. Another one would be a uniaxial stress, where you allow this to be a free surface, so zero stress, but you'd expect that probably as you compress it, it would expand this way. It turns out if you do that with our material, that doesn't ever put it inside of the twin regime. So if you just do uniaxial stress on this material, it will never do something like this. You have to have this fixed boundary condition here in order to get something like this. You have to constrain the material in the other direction as well. Yeah. But good question. Yeah.
I'll make a random question for this one. Would you expect any different behaviors if this was a dynamic loading, for example, like a sort of propagating wave with a pretty large wavelength? Will you, I don't know if there's anything that can be almost stabilizing effect on the inertia or something.
Right. I don't have a lot of intuition. I can say what intuition I do have. So the fact that this material is perfectly soft and shear in this domain will mean that if you try to propagate a shear wave through this material, it wouldn't get anywhere. Because there's no shear modulus to drive that wave to propagate through. That is the case as long as the magnitude, the amplitude of your shear wave is sufficiently small that you never leave the twin regime. Because as we saw, once you get out of that regime, you again have a finite modulus. So if you send a big enough amplitude, it could maybe propagate a little bit, but if it's small enough that you stay in there, it wouldn't. Of course, the way we're modeling this isn't taking into account dynamic behavior at all, viscoelasticity of the matrix, which you'd expect in real life. So if you did things dynamically. So how that all plays into it, I can't say, but that's at least one thing I can say.
So maybe just to follow up on that question. To what extent, if at all, do the material properties come into your models? I mean, you're discussing elastomers, but the property of elastomers can vary a lot, and
Right.
I mean, you said this was
Right, yeah.
which is still there, even if you do some kind of fuzzy side, you might have some of that, right? So what do you think? Is there some input, or could you maybe change this behavior by changing the properties of the material?
Presumably, yes. So this is like the simplest possible type of behavior that we can assume from matrix. It's incompressible and it's neo-Hookean. There's only one parameter, mu, governing everything. There are other results that people have computed for maybe slightly more general types of matrix behavior where they still see this loss of luticity. So that sort of general behavior I would expect to be in other types of systems. The details might change a little bit. If you made the matrix compressible, I would expect that would also change things, because I think the incompressibility of the matrix is something that's very important. You know, basically the pores don't want to close all of the way, and I think that's what's making the material want to shear instead of closing the pores completely. But if you allow the material to be compressible, it doesn't have as much reason to resist that. So I'd expect that would again change the details. Yeah, and then if you start introducing other types of mechanics, say viscoelasticity, start computing dynamic behavior, that makes things different again. That's one thing I can say. Another thing I'll say is this behavior is specifically due to the way that we lost strong luticity. So you could lose strong luticity different kinds of ways depending on how your energy is behaving. And so loss of luticity does not necessarily lead to this type of response. It's also something that people will use in metals to signal shear banding. So you can get these layers where, essentially the thing that's energetically most favorable is for it to start localizing the shear onto a particular band. That's something more associated with metals, but that's to do with the way that the energy is behaving around there, the way it softens and stiffens in various directions. Yeah.
Maybe Peter, I can ask one question.
Okay.
It was kind of the presentation by showing results for, and these are experimental results, right? For periodic elastomers.
Yeah.
And you saw this pattern transformation.
Yes.
From something that's periodic in one cell, something that's periodic in maybe 2 by 2 cells.
Yes.
Right?
Yeah.
And by the way, it's important to emphasize, I think you did say that in the presentation, that this result experimentally has been obtained by many different groups. So it's an interesting result, but it was predicted theoretically several years before it was actually observed experimentally. So there's hope for this.
Maybe this actually does happen.
So that's the first thing. But the question then is, okay, so if the microstructure is periodic, you go from something that is, you have a change in periodicity of the pattern of your solution, right? Here, the microstructure is random, right? So we don't have a period.
Yes.
So how can we understand this domain information in terms of pattern transformations? Is there a connection?
Well, so if you look at a periodic system, loss of luticity would be an upper bound on the point where you could have this type of instability. But in general, for a periodic system, you could have an instability that occurs before that, which would correspond to this pattern transformation. Essentially, when you, well, I'm talking more to them than to you know all of this. But if you're doing periodic homogenization, the simplest thing you can do is just choose one unit cell where your material is periodic and see what happens to that unit cell, and then just assume that the material behaves like that unit cell, just multiplied by all directions. So you have like periodic boundary conditions applied to the unit cells. But that's an assumption, and what you can see from there is that could be, the result could be periodic on 2 by 2 unit cells, or 2 by 1 unit cells, or 3 by 2, or any sort of size of unit cell that's larger than that is also a possible solution. And that's what that pattern transformation there corresponds to. It's the first point where you get something that's periodic on a supercell that's more than 1 unit cell, where the material is periodic. But that relies on the periodicity of the material. So if you start breaking down that periodicity, you start to not really be able to have this type of pattern transformation. And so as that periodicity starts to break down and you approach something that's random, you start to approach something which has these what are called long wavelength instabilities, which is where you have this large separation in length scales between these layers, let's say, and the length scale of your microstructure. Whereas for that pattern transformation, the length scales are of the same order. Yes.
Question.
Yeah.
So in structure, so you have poles, and the poles are like non-periodic, right?
Right.
Is it possible that if you just like keep increasing the size of the periodic array, at some point a certain region will be a periodic unit cell? Like inside this material?
Yes. And in fact, so this is an approach that some people use for doing random homogenization is treat it like a periodic material where you have a unit cell where that unit cell is kind of disordered. And so maybe approximately it behaves like that, like a random thing, but where you can use the periodic homogenization kind of technique. So maybe you do FEA on this unit cell that looks random and then just assume the results of that would apply to your whole random microstructure. Is that where you're going with the questions? Okay, yeah.
In principle, that's the right thing to do. But in practice, we're talking about those types of relations and et cetera, it's not an easy computation with, sophisticated methods.
Yeah.
All right, if not, then here. You guys point out, you will get from the department.
Yep.
The quotations funded.
Thank you very much. Yep.
I would suggest, at some point you guys have did one of these. President Franklin was the founder of the University of Milan. He was very interesting person, he was not only a politician, a businessman, but he was also a diplomat, but he was also a scientist. There is a biography of President Franklin, I don't know if you've seen it, yes. And I strongly encourage you to read that biography. Maybe so I don't get in trouble with your wife.
Thank you. Thank you.